Okay. Hello, everyone. Welcome to the November Recreational Astronomy Night meeting of the RASC Toronto Centre. My name is Paul Markov. I'll be your host for this evening, introducing the speakers, and also hello to our viewers on YouTube. The lineup tonight includes Andy Beaton presenting The Sky This Month, followed by Denis Gray. He'll talk to us about new Occultation technology showcase. Charline Norgrove will talk to us about the Hoba Meteorite in Namibia, Africa. And we'll wrap up the speakers lineup with Artash and Arushi Nath that will talk to us about a deep space musical, transforming iconic Hubble Telescope images into music to create a musical of the universe. So I think we've covered everything. Oh, one more question is for members here, rather for people in the audience. Anybody here for the first time, member or not? Show of hands. So everybody's been here before. One? Oh, hello. All right, welcome. All right, so without further ado, I'll call on Andy Beaton to present The Sky This Month.
Okay, is the sound working? Yes. Hello. Good to be here again. Unfortunately, it looked like another cloudy month ahead of us, but we'll assume the skies are going to clear up and everything's going to be fine. Tonight is going to be a bit of an embarrassment for me. A long time ago, Denis Gray asked me to cover for him on a Sky This Month night, and I shamelessly stole his template, and I've been using it ever since. And my
copyright notice at the bottom there.
Yeah, my theft is going to be exposed in front of the entire internet, and but there we are. So what we have tonight: the big picture, planets, the moon, bit of a digression into spiral galaxies, comets and meteors, variable stars, obviously. Double star. Is Blake here? I can't see in the darkness out there. If he's not, he's probably watching online, so he knows I remembered. And some spaceflight highlights. So starting, this is what the sky looks like behind the clouds. If we look to the west around now, we can see the summer constellations are slowly disappearing. But we can still see a few planets there. We've got, is this working? No.
Use the pointer. Use the laser. Just point with the laser. Yeah. Yep. Press that.
Hey, how do you like that? We've got Saturn still visible above the horizon, Pluto, Mars, Neptune, and Uranus. So there's still some planets to be seen. Still some Milky Way to be seen. We've got the summer Milky Way just about directly overhead if you're out early enough. If you stay up late enough till the morning, we get the summer constellations starting to appear. Bootes, Corona Borealis, Hercules, and all that gang. Not a lot in the way of exciting planets in the morning. Venus, I guess, is the big one. Ceres is going to be just barely visible. And for those of you with giant telescopes and great patience, a couple of the more obscure minor planets way out there. The nights are getting long. Twilight ends at 6:22. And starts at 5 in the morning. By the next meeting, twilight will end at 6:05 and start again at 5:42 in the morning. So that's a lot of imaging time for people who need long exposures. It means you can take your telescope out, see a few good things, and get back inside before dinner. So lots of observing time coming up, weather permitting. Important dates, new moon is today, full moon, another full new moon coming up December 7th, The moon is at apogee on November 14th and perigee on the 26th. As always, I encourage people to take pictures of the moon at these two occasions so you can compare the size. It's always an interesting experience. Pluto will be occulted by the moon on November 12th. We're not going to see it from around here. If you're traveling up to the northeast corner of Canada or up around Greenland, then you'll get a chance to see it. I personally wouldn't recommend the trip, but it's going to be hard enough even finding Pluto. November 18th, we've got the Leonid meteors, and Venus's greatest illuminated extent on December 2nd. So if you want to be up in the early morning showing people the brightest thing they can see in the sky, that'll be Venus that day. So the moon, new moon coming up on tonight, another one on December 7th, full moon on the 23rd, if you want to plan around that. Lunar X on November 15th at about 4 in the morning. I'm guessing most people here know what the Lunar X is, but for people who don't and people watching on the internet, it's an interesting intersection of craters, which if you look at it at a certain time, makes an X. It's not scientifically important, but it's a cool thing to see, and it's fun to look at. I'm not sure I would get up at 4 in the morning to see it, but if you're up at 4 in the morning for your other observing programs, have a look. It's a cool thing. So the planets we have coming up, Mercury and Venus are the morning planets. Mercury is going to be pretty lousy unless you have a really good horizon. Even then, it's hardly going to be worth the effort. Early December, it will improve. It'll be visible anyway. Venus is the morning star. It's rising and getting brighter in the morning sky. Right now, it's a narrow, close crescent. It's just about as close to us as it's going to get, and it's receding away from us, but the phase is increasing, so it'll be getting considerably brighter. Ceres and Jupiter are also up there. Ceres is good because it's the best of the minor planets. Not many people have seen minor planets. Everyone knows about the big controversy about Pluto. There was actually the same controversy about Ceres and Vesta way back in the 19th century, so this is your chance to dig into some astronomical history and find the controversial object of past times. Jupiter will just kind of be appearing right before dawn. Not a great view yet, but the fun thing about Jupiter is it stays visible into the day, especially if you have a telescope, so you'll be able to track it then. Ceres will be early December. Ceres will be pretty close to Venus, so if you want to go looking for it, it'll be a good time. You'll have that marker in the sky. In the evening, Mars is the thing everyone's going to be looking at. It's not its best viewing right now. It's about 11 arc seconds across, which is pretty small. However, given that when it was at its opposition, it was all covered with dust anyway, you're probably going to get a better view of it now than you did then. Should be able to see the ice caps in small telescopes, medium or large telescopes. You'll be able to see all the other surface features, Syrtis Major and all those. So Mars is probably the best thing we've got to show off to people if you have, if you've got friends who want to have a look at the night sky and you need something spectacular to show them. The other outer planets, Saturn's just disappearing into the sunset. If you have a good western horizon, you may be able to show your friends the rings, but the seeing is going to be lousy. You're not going to see anything interesting there. I doubt you'll see the Cassini Gap or any weather. Pluto's in Sagittarius. It's hopeless. It's too close to the horizon. It's too light while it's up any higher, and it's almost impossible to see when it's that deep in the Milky Way anyway. Neptune and Uranus are better placed. They're actually, if they were brighter planets, they would be outstanding for showing to the public. Anybody who's seen them knows that in any amateur telescope, they're really not that spectacular. They're just kind of a small greeny blue disk. I would suggest that people go out and compare them. Everyone tells me that Uranus is blue in color and Neptune is green in color. And I'm never really sure whether that's just a power of suggestion or something they've read in a book or actually gone out there and observed it. So if you get a chance to compare the color of those two planets, give it a try. I would be interested to hear what results you get. And Eris and Makemake are out there. I suppose it is technically possible for anybody here with the largest telescope and the most powerful CCDs and great patience to actually get an image of them. If anybody does so, let me know. I will post your picture up here the next time I'm doing the sky this month, and everyone can clap for you. So I always like to throw in a bit of deep sky stuff for people to look at. Local spiral galaxies are up now, M31, M33, and all the little galaxies that follow Andromeda around. For those of us stuck in the city, they're terrible targets, even though you can see the center of M31. If you can get out of the city, then you've got something worth seeing. I'm going to suggest people take a look at M31. I mean, everybody's seen it. Everyone's seen it a million times. It's the first thing you point your telescope out at when it gets dark at night. But there are more things to see in it than just seeing the galaxy. Beginning observers, seeing the galaxy is enough. It's pretty spectacular. For more advanced observers, looking for the dust lanes, looking for the giant superclusters, the stellar associations. Really advanced observers can go digging for globular clusters, or even trying for individual stars. 16.5 magnitude is the brightness of the giant Cepheids that they use to actually determine the distance to the Andromeda galaxy. 16.5 magnitude is not out of reach of more than a few people in this room. So if you feel like an observing project, you can actually measure the brightness of those stars and calculate the distance to the Andromeda galaxy. That's a project that would actually be really impressive to achieve. I can't do it. My telescope's not that good. And yeah, there's M31. Everyone loves it. M32 and M110 in there as well. I always remember M32 is the close one because the numbers are in succession. And yeah, you can see a bunch of the bright stellar associations along the rim there, and some of the brighter nebula along the other edge there. So yeah, there are targets available for people with a taste for the more exotic, even in something as common as M31. So comets and meteors coming up. The Leonids are peaking on November 17th. The moon is up until 2 a.m., so if you're going to go looking for them, you'll want to stay up pretty late. It's a one-night shower. There's not going to be much before or after, but that's really all we've got until the next meeting. Now, 2 days after the meeting, then we have the Geminids, and that's a shower worth seeing. So keep that in mind for the future. We have 4 comets, reasonably bright and improving: Stephanoterma, Wirtanen, Swift-Gehrels, and Atlas 2018. Wirtanen is actually pretty far south, pretty close to the horizon from here, so it's not an outstanding target. Atlas 2018 in Ophiuchus is going to set pretty soon, so if you do want to observe, get out there and see it as quickly as possible. And 21P Giacobini Zinner is still out there. It's fading, unlike the others, but it's right there in Canis Major, which makes it a nice, easy target once the night starts getting on. So for variable star this month, I've picked Beta Persei, which we all know as Algol. I picked this one because it's actually pretty accessible. It's an easy one to see. There's a mention of every minima in the observer's handbook, so you'll be reminded when to get out there and observe. Every 2.8 days, more or less, it drops over a magnitude, and there are nearby stars of roughly equivalent brightness, so it's a pretty easy observing target. It's what you have is a faint dim star eclipsing the bright primary. So when the bright primary is blocked, the magnitude plunges pretty dramatically. When it goes the other way around, when the bright star is passing in front of the dim star, it's not so much of a spectacular event. You need a photometer to be able to measure that. What's interesting about this, and the reason I suggest people get out there and observe it, is the period has been changing. Over the past century, it's actually increased in time. The orbit of the two stars around each other is slowing down. So if you're the kind of person who likes to get out there and take as accurate as possible measurements of stars changing brightness, gathering data on eclipsing variables and not just Algol but other equivalent stars is useful data to professional astronomers. Looking for a good double star, Alpha Piscium is one that I had a good deal of fun with because it's a very narrow double. I actually had a really hard time splitting it, and actually I'm not sure my scope was sufficiently columnated because I didn't split it. I just got it as a kind of elongated double blob. But with maybe a slightly better eyepiece, maybe a bit more patience in collimating your telescope, it should be splittable by any reasonable telescope. I also find it interesting because its orbit is really fast. It seems to be going around at a rate of about a degree a year. So that's actually enough to record and go back in a few years' time and see a noticeable difference. So it would be a good long-term project to observe this one as it goes through the years. So coming up in the world of spaceflight, Falcon, more Falcon launches. I'm not even going to bother watching them unless they promise a landing. I still think the landings are cool. Launches, I don't know. The interesting thing to me is what's going to be happening with Soyuz. As we know, the last astronaut launch aborted halfway up, and the astronauts returned to Earth through some peril, not entirely a safe process. So the Russians have promised that there will be 3 successful flights of the rocket before they put humans back on. In the meantime, the astronauts are stuck up on the space station, so it'll be very interesting to see what happens there. The space station will be passing overhead in the morning until November 15th. Then for a while we'll see nothing, and then November 24th until mid-December it'll be passing over in the evening. It's always a good target to get your friends out to have a look at it. Everybody likes seeing astronauts flying over in space. Heavensabove.com has times and locations, which you'll be able to look up for yourselves. The Hayabusa 2 probe orbiting the asteroid Ryugu. They've got a couple landers on it, and now they're having some close orbits preparing for the next set of landers. Keep an eye out for interesting data coming back from there and showing up on the internet. Next question, the Opportunity rover. As of 2 days ago, they were still trying to contact it. NASA hasn't entirely given up on it. But the longer it goes, the worse the odds they're going to recontact it. So keep an eye on the news there and see what happens. We know that this has been a bad month. Both the Kepler and Dawn probes have finally run out of fuel and have finished their missions. But on the upside for astronomy, and I'm not going to go into the politics of it because it's ugly, but the 30-meter telescope was okayed by the Hawaiian Supreme Court, so we'll see what happens there. And I guess the other item in the news this past month that needs to be discussed, we all know about this, Kamehameha. Somebody from Harvard University has come out with the opinion that this is actually not an asteroid or a comet from an extrasolar location, but actually a solar sail-powered space probe come to have a look at us. Is this true? No, it's almost certainly not true. I feel confident in saying this because if it turns out it is a solar-powered space probe from another solar system, nobody will ever remember that I went and contradicted that. But over the next month, keep an eye on it. If it turns around and comes back for another look, then we'll know that I was wrong. So thank you very much. And are there any questions?
And did you have any information on the object that is getting close to the sun? The object that is approaching the sun?
I do not, no.
There's a spacecraft that is supposed to take measurements very close to the sun.
Oh, right, yeah. Sorry, I missed that one, yeah. Yeah, we'll keep an eye out for that, too.
What information can you give about the status of the dust storm? I haven't looked at Mars for a while, and is it worthwhile pulling my scope out again?
That's an excellent question. Whenever I look at Mars, whenever I've been looking the past month and a half, what I actually see is clouds. So I can't tell you what I've seen on Mars recently. I'm told that the dust storm passed late summer, August, early September, so it should be clear now. I haven't heard of anything coming back. So next clear night, take your telescope out and have a look. Yes, May.
Hopefully not.
Okay, thank you very much.
back. Thank you very much, tech team, for getting us back on. So my name is Denis Gray, and I'm going to be talking about new occultation technology and giving you a little bit of a rundown on what I've bought recently. But first, I want to talk a little bit about, thank you, what are occultations in the first place, or not everybody's probably familiar with it, and I'll talk about the quest. So it's kind of like anybody who's interested in occultations has this nirvana that they seek. They seek to be able to go out, plunk a telescope somewhere, have it automatically find the target, and then just observe whether or not it turns out or not. That never works. So we'll talk about what we're actually trying to do and what kind of the ideal system is, and then we're going to compare and contrast two opposite pieces of technology. Both are recent. One I'm calling cheap and cheerful, and the other one I'm sort of calling all-in-one or next generation technology, and we'll talk a bit about that. So first and foremost, what are occultations? So an occultation defined is an event that occurs when one object is hidden by another object that passes between it and the observer. An example of this would be, hey, that 2017 occultation of the sun by the moon was a very big event. And not everybody calls it by its proper name. Some people have been known to call it an eclipse. But it is an occultation by definition because it's hidden. And I think one of the key words in this is event. It is an event. This is event astronomy we're talking about here, and we'll talk a little bit about what's involved with that. Now, in terms of astronomy, we have many flavors of occultations. There's not just one. It's not just that one that is also known by eclipse. But generally speaking, the moon gets involved a lot. Many times during its monthly orbit, the moon will run over stars. You can see here's a frame grab from an occultation, and that star there is just about to be run over by the edge of the moon. And when it does, it blinks out. It blinks out because the star, at the distance that it is essentially a point source. If you look at it in a telescope, it looks like it's not quite a point source, but at the distance it is compared to the moon, it is a point source. So it's like basically a tiny little extremely bright pin on the edge of the moon, and as soon as the moon's edge goes over it, boom, it's gone. So from one frame to the next, you'll see most stars will blink out immediately unless they're an extremely large star like an Antares or something like that. The other flavor of occultation of stars by the moon is what they call a grazing occultation, where a star sort of just edges through the North Pole or the South Pole of the moon. And what you see there is lunar topography revealed, in the sense that hills, valleys, mountains, and so forth will cause the star to blink on and off. And this study, for many, many years before we had lunar satellites that measured the moon to within millimeters precision, was our best way of understanding what they call the lunar limb profile. And some people still do those occultations now. We also can see the moon running over planets. That's kind of a cool event to watch. So you'll see Saturn get closer and closer to the edge of the moon, and then it'll take out one half of the rings, and it'll take out the planet itself, and then the rings finally disappear, and then in reverse. I've seen Venus get occulted by the moon, and that's actually a cool event. You can actually observe that with the unaided eye, where you see this really bright planet being run over by the crescent moon, and eventually it blinks out. But it will, because the Venus is actually relatively large compared to the edge of the moon, it actually takes a bit of time to go away. The other really interesting one is sort of occultation of planets by other planets. This is actually something where you need to have exactly the right geometry, where a planet like Uranus will be occulted by another planet like Saturn. So first of all, they've got to be close in their orbits to even have a chance, and then it's got to be, Earth has to be in exactly the right place where everything lines up. So there's like 3 or 4, 5 events like that per century, and you can look up those, and if they're I'm not sure when the next one is coming, but those are pretty exciting. And then also another occultation flavor is mutual occultation of Galilean and moons. So what happens is when the Galilean moons are precisely aligned with Earth, which happens in 2 seasons separated by about 6 years, when those moons cross each other, you'll see brightening and dimming of those moons as they essentially overlap one another. And our favorite, and the one we're going to be mostly talking about tonight, asteroid occultations. Now, asteroid occultations is a branch of citizen science. It's one of the remaining areas in astronomy that amateurs are really able to make a big contribution. And in fact, most of the research that's happening here is either participated in by amateurs or driven by amateurs. One of the big projects you probably heard about is New Horizons recently. New Horizons was trying to pick its next target. So one of the opportunities was to use an occultation of a Kuiper belt object that was able to pinpoint that object's position and help determine where New Horizons is going to go next. So when you're observing an occultation and you're doing the timing, we can add these little pieces of information to what we know about the universe. And that's sort of the definition of science. It's an incremental thing, we're adding a little bit. But by knowing when that event happens, we can use mathematics and other information to determine exactly where was the star at that moment of the occultation. Similarly, we also know exactly where the asteroid was at the moment of the occultation. And using that information, along with some other stuff that we have, we can determine the shape, size, as well as sometimes the volume of the asteroid, which leads to its density, which leads to, and combined with its spectra, leads to information about the origins of that asteroid. So all of that stuff is coordinated by a group of passionate amateurs at the International Occultation Timing Association. They have an annual, I think they have $10,000 in their bank account and an annual budget of $3,000 or something like that. It's truly a labor of love kind of organization. So why is this fun? Well, it's event astronomy. It's astronomy as a sport. In order to observe an occultation, you have to be in the right place, the right time, and you need to have the right rig. So it's essentially putting together all of your skills, all of your experience as an amateur astronomer to try and pull all that together. And what I've noticed is that the universe does not wait for you. It will go ahead and it will do the occultation exactly when it wants to, whether you're ready or not. And that is sometimes frustrating. Sometimes it's extremely frustrating, but it is essentially the nature of the sport is that sometimes you succeed and sometimes you fail. The best events are tracked through IOTA and its members and their participants there. And generally, what I'm looking for is a reasonable time. I'm not one of these people who's ready to stay up till 3:30 in the morning to do this. My work life is too much. It's got to be a relatively bright star, so it's relatively easy to spot and find. And ideally, you want to have a good magnitude difference. So you can have an asteroid occultation, and you can have an asteroid occult a star perfectly well, but if the asteroid is 11th magnitude and the star is 11.1 magnitude, well, you're not really going to notice much of a difference there. So that also makes a difference. And then, all of these things have to be put together, and sometimes you'll find that the universe will conspire to give you 3 events in 24 hours, and other times the universe will conspire to give you no events in 3 months. And then you have to, of course, add the weather factor, which I think is threatening this week's really good occultation, and so on it goes. So it's part and parcel of that process. So the objective when you're trying to measure and observe one of these occultation events is to get your location on Earth, your disappearance or perhaps a dimming time precisely, and a reappearance or rebrightening time precisely, and submit those 3 key pieces of information to IOTA. They're going to collate your observations with other people's observations, and you're going to end up with something that's like this. So here you've got a whole bunch of individuals with a whole bunch of telescopes all looking at the same event at different times. So this one here, this bright blue line, they could have been in Europe. And this one here, this yellow one, they could have been in California. This one here, I would say they're in Hawaii, but that's not possible because that would have been daytime. But in any case, all of these observers spread out across many, many different locations, but we know where they are relative to this asteroid's shadow that's basically passing across the Earth. And when we put all their disappearance times and their reappearance times, so this has disappeared here, reappeared here, disappeared here, reappeared here, we're able to get a shape of the asteroid in 2 dimensions. So this is one of the most successful ones that's been done in the recent times. So this is a binary asteroid. This part of the binary looks, fairly round-ish. This one, it's got a huge divot taken out of it, and that's one specific, sort of slice through these 2 asteroids on a specific date and time. And if we're able to combine this information plus other informations, you can actually over time build up a 3D profile, because one of the other things we know about this is the rotation period of these 2 binary pieces is reflected in the light curve that comes from the asteroid. So you put all this information together, we can learn an enormous amount about these objects without actually really being able to see them, which is kind of cool. Although I would love to see a space probe go and visit this system, because I think it would just be the coolest thing to see these 2 rotating through space. I'm sure it's a bit of a mess. So that's the objective. So how do we get there? So you need GPS level information. So in order to know where you are precisely, you need to have some GPS information, which is your latitude and longitude on Earth, precise location, and you need to have precision in time. So all of those measurements that we're looking at here, the reason they're so nicely coordinated and they're so tightly cut off here is GPS level measurements. You need some optics. You need to have a telescope. Generally speaking, a shorter focal length is better than a longer focal length because you get a bigger field of view, and the light from the stars is concentrated onto fewer pixels, which allows those pixels to give you a better signal to noise ratio. So you're able to see when the asteroid dims or blinks out. So that's something to keep in mind. And then you need some sort of recording mechanism to put all that information into a place so that you can record the ins and outs and so forth. Now, over time, the state of the art has changed. So when I first got into this back, early in the 21st century, the essential process was you're going to use a map. You're going to go and get a topographical map, and you're going to go and find the location of that country road where you were at the 4th concession, or was it the 7th concession? I can't remember now. And you're going to precisely locate yourself roughly within, a couple hundred, maybe 100 meters. That's, of course, moved towards standalone GPS devices, and now everybody's pretty well got a GPS on your phone. So you can get very, very accurate location information. Telescopes, obviously have been revolutionized in a lot of ways by go-to technology. So the dream is that you can plunk the telescope down. In some cases, you push a button or you turn it on, and it will figure out where it is, and it will come up and be able to point to the location of this event very, very quickly. Video technology has changed very quickly, and when we first started to work with occultation technology, we were always using analog video, and analog video was pretty well limited to sort of the screen size of the day. So the PAL or NTSC standard was sort of like 640 by 480. That was a standard 4:3, what your old television would have looked like, and that was part and parcel of that whole analog technology. We moved partway from that by recording this analog signal on a digital video method so that we could translate it more easily into computer language. But now we've moved towards pure digital video recording. So now all of your cameras, like if you're using a camcorder or DSLR to do recording, you're recording digitally, and there's no intermediate analog video happening in between. And then in terms of recording, it used to be that people would have a voice tape recorder and they'd be listening to a time signal from Colorado beeping on the radio, and they would say, out, in, and then they would go back and they would have to interpolate, exactly when did I say out and when did I say in, and knowing that I'm a little slow in the uptake. I have to add 0.2 seconds to that because that's my personal, what we used to call a personal equation, to record the time that these things would happen. Because all of this was done visually at the beginning. So what's now happened is we've added video overlay systems to add that GPS information to the video. And what we'll be talking a little bit about tonight is integrating all of that together into one camera. So, how many of you are excited? Want to get into this? Yes? Sure, thank you. All right, so cheap and cheerful. You want to start cheap and cheerful. So there is a new offering kind of thing that's been put together by our friends at IOTA, the International Occultation Timing Association. They're all about encouraging people to get involved, and they have their own emailing lists, and they promote events, and they're generally a very nice group of folks. And they have created this thing called the Night Eagle Astro Camera Kit. And it's based on an interesting camera. I've never heard of it before. I happened on this, which is a night vision drone camera. So this is an extremely lightweight camera designed to be absolute minimum weight, run on a drone, and go over people's houses and spy on them in total darkness. So it's got really, really good response and so forth. So essentially, the folks there identified that it can do integration, which means stacking frames up to 16 frames to intensify the signal-to-noise ratio. And IOTA's put together a kit for $179, which is essentially giving this little cheap and cheerful camera here, this kind of off-the-shelf camera. And what they've done is they've put together all the little bits and bobs and spacers and a focal reducer and so on to allow you to install it on your telescope. So this is what the finished camera would look like, and this is all the bits and bobs that you would get in the package that would allow you to do that. So the overall kit is available from IOTA. They actually will sell it to you, and they'll ship it to Canada and everything like that. So this is sort of the state of the art for cheap and cheerful. Now, before this camera came out, you could also get other video cameras that would be, this is an analog video camera. You can get other cameras, kind of similar price point, but what I think is really exciting about this one is the sensitivity's just gotten better and better and better. So they're getting like 11th, 12th magnitude with, reasonably inexpensive scopes using these kinds of cameras now. So that's really, really exciting. The other thing you need with a cheap and cheerful system is the video time inserter. So we talked about the need to know your GPS time as well as your GPS location. And what it does is it takes your GPS information and it overlays it right on the video signal so that the video output has already got the timestamp put in there. And the limitation is going to be the precision of the video. So the timestamp is going out there as fast as it can, and the video is running at 50 frames a second or 60 frames a second. So that's sort of your time resolution. Is you can't get any more fine than that. The universe is a little bit more, has more precision available for it, but that would be that. And then you need some sort of a video recorder. Now, one option for recording this video as it's happening is a DV camcorder, digital video cassettes, and those have kind of fallen out of use pretty well. They're not antiques. They're still kind of high tech, but you certainly can't buy a new one. But you can still get some of them available on eBay. Now what IOTA's recommending is that you go to the field with a laptop and you have a USB video capture device, and they have a specific package of software, most of it free, which allows you to keep your video streaming into your computer and not lose any signal due to compression. So a lot of video software will look at a picture and say, most of that picture is black with just a few spots on it. So I'm just going to scrunch all that down because it's just mostly black. And that's not what we want, because that's the part we're interested in, is when does it turn black and when does it not turn black. So that process of using that, and there's some technical guidance and so on, lots of helpful information there. And you follow that helpful instructions and you'll get pretty high resolution with that. The other piece, and the cheap and cheerful option, is you need the analysis software to sort of read this video file. So you record this video file, you dump it onto your hard drive, and it's like, okay, there it is. Now what do I do? So what you do is you open up in this program called Tangra, which is freeware, and it reads both AVI files, which is a common video format, and then this astronomical video format, which is being worked on here. And that Tangra can actually read the timestamp from the video time inserter, and it will actually give you an analysis of the disappearance and reappearance. It will actually show if it's a step disappearance, which can sometimes happen if you've got a very close binary star, and it's free. It's very, very cool software, and well done. So that's cheap and cheerful. So if you want cheap and cheerful, that's the option. Now, the new option, which I purchased recently, is the next generation sort of video option. So this is a specific camera from QHY called the 174M GPS, which is a much larger imager. So this is 1920 by 1200 pixels versus that's kind of a large video camera. 640 by 480 is also possible. So it's twice or 2 or 3 times as big, but it means like 4 or 5 times as much resolution. It's using USB 3 video, so it's actually recording on it's taking advantage of the fact that USB has a much faster rate of data transmission than USB 2, and so it allows it to actually transfer these large files at high rates. It's fairly heavy. It's about a half a kilogram, 1 pound. And the frame rate that it does, as opposed to a video, where a video frame rate is 60 or 50, whether it's got anything to show or not, that is the definition of the analog standard. So depending on whether it's NTSC or PAL, you just get the frame rate you get. Here, the frame rate really depends on how fast the frames are being received by the computer. So you can tune it to get the frame rate at the best possible combination of frames and recording to suit your computer. So theoretically, you can get much, much higher time resolution on these events than you can get with an analog system. And then because it's got this bigger imaging thing, it also has a bigger attachment, which is an M42 or a T2 thread. So now I said to Paul when I put this presentation together, that we would have a chance to, show some stuff here. And I received this about 10 days ago, and as most of you know, we have not really seen the sky at all. And so I have verified that this camera, when plugged in, works. And I can say for a fact that it will image stuff when it's plugged in. That's the extent of my testing now. However, other people have had better luck than I've had, and this is a sample of the output that you would be able to get. So what you can see down here is, essentially the time signature here, and that's, the hour, minute, second, and partial second there, and between the 2 frames. So this event happens, in there, and this is an example of some integration going on. So he's actually taking a bit more time to get more sensitivity, and he's getting down to 12th or 13th magnitude stars here. Some of these more dim ones are very, very sensitive. And you'll notice that the quality of this image is a little icky. If I was an astrophotographer, I would say, well, this is garbage. I'm going to throw this out because obviously I can't stack that or do anything with it. From an occultation perspective, you really don't care. The point is, does that disappear or not? And if it does, great. If it doesn't, that's also data. And so you're simply monitoring to see whether it disappears or not. You're not so concerned about whether or not it's pretty or not. Now, it is important that the stars be, your telescope be well collimated, that the stars be, focus up crisply and so on, but that's all about seeing what you're trying to see. And this shows us the actual frame count that's being imaged here in terms of the frame. So you're seeing good, results here. It's going deep, and this is big. Like, this is actually, quite a big field of view, and I'm going to hopefully get some measurements of what that looks like. So this is what it looks like. the camera, and we'll have a look at it a little bit out there. So this is for those of you who are CCD imagers, this is actually a variation on an existing QHY model. So there's another version of this that doesn't have the GPS option, but is essentially the same kind of camera. So on the back here we've got the USB 3 port, we've got a power port for running the thermoelectric cooling, we've got a filter wheel connector, we've got a guide port. So all of that stuff is standard, and then what happens is if you buy the GPS model, you get this little GPS antenna mount here added, and then that becomes the key difference. That plus some additional electronics in it is the difference between the GPS unit and the not GPS unit. So as astronomical video cameras go these days, 2.3 megapixels is pretty small, but still useful. You can still do a lot of good things with that. So drum roll, please. Let's look at the money piece here, because that is important. So the cheap and cheerful option, if you don't have a timing unit, so it's about $500 US. So there's bits and bobs you need to put all together. And thanks to Steve Conrad who put this comparison together, looking at that. So you have your basic camera, you have your GPS, you've got your cables and so forth, and you can then essentially work with that in the field. And I have an example here. This is my rig from before, where I have my field unit that I would use to do analog video recording in the field with a camcorder, with the screen, the monitor to see what's going on and so on. Now the QHY GPS here, the camera is a lot more expensive. The GPS timing is built in though. The power supply is not required because you can run this off of your computer using the USB port. There's no video input required, so you don't need any of that. The focal reducer is going to be bigger because the camera is bigger. So you can use a very small focal reducer on the small cameras, but for these larger cameras you need a bigger focal reducer, so you need to spend a little bit more money on that. So we're looking at about 1.5 times more to get this sort of next generation technology. And the key difference really is its usefulness for other astronomical applications. So my goal for this is not to have to take the whole case with me every time I want to do an occultation, that I could actually go and do some imaging type applications with this, and then when an occultation opportunity presents itself, just turn on my GPS option and let it go. It's somewhat future-proofed in the sense that this is digital imaging, I think, has reached a certain point of maturity where I don't think the formats are going to change that much. It's producing FITS files, it's producing an SCR file, so I believe that the output from the camera, no matter which one it's doing, should be there. But the price difference, 1.5, 3 times more, depending on what you're going to do. So that is one of the big differences there. So you've got a much bigger camera, all digital, smaller footprint in your equipment case, but you're going to have to spend more money for it. So that becomes the key thing. So I'm just going to ask you to turn up the lights here, and I'll just sort of show what this looks like. So this is my occultation camera here. So right here on the front. Now I'm using a C8 here, which has got a hyperstar lens on it. So one of the things that, if you know how a Schmidt-Cassegrain works, and normally the light comes in here, hits the mirror, hits another mirror here, and then goes out the back. And that system is an f10 or an f6.3. Now with a hyperstar lens here, what happens is it comes in, hits the mirror at the back, and then it hits a lens here where it's corrected, and then it comes out the front. So the camera is mounted on the front, and it looks a little ungainly because I'm always thinking, well, if I just do this, I'm going to break my corrector plate on my camera, and that will be the end of that particular telescope. So generally in the field, we always wrap this with a dew shield in the field. But the idea is that you have this camera which actually doesn't add very much at all to the central obstruction. It's like literally almost exactly the same footprint as the mirror originally was. You just lose a little bit, and then you've got your cable coming out the side, and that's it. So it works as a system. And the cool thing is that it's a very very fast system. It's f1.9. It's a 390 millimeter. It's like basically you're getting this big, big telescope, and you're getting, you know, what amounts to telephoto lens style f ratios. So the theory, and one of the things I would hope to measure and share with you, is just how big a field of view I can get with this camera combined with that that telescope, with presumably some proper spacers included. So, as I said to Paul, there's probably another presentation in this somewhere. So then that telescope with that camera mounted on a go-to mount and attached to a computer, which will give me both the video and the telescope control, represents a significant reduction in the amount of stuff that I have to take on the field to actually do what I'm hoping to do with in terms of measuring occultations. And that's kind of my goal. That's what I was hoping to get for it. Don't know if I'm going to get it necessarily yet, but hope springs eternal. Conclusions pending. However, if we get some clear weather, I'm hopeful that we will have some conclusions that we will be able to share with you, and I'll try and post some of those on the list, and hopefully one of these days I'll actually even have a chance to actually record an occultation and maybe put that on the line somewhere and share some results like that. So that's what I got, occultation technology today. Yeah. Any questions? Yeah. Ooh. Yes, sir. Mr. Beaton.
How much of a big deal is it to replace the secondary mirror on your telescope there with your camera and widget?
It's pretty simple. It's got a locking collar. You basically unscrew that, and then you unscrew the protective cover from the Hyperstar, and you put the Hyperstar down. You put the mirror in the Hyperstar dingus, and then you screw it tight, and it's locked and it's dust-proof. And then you put the Hyperstar mirror and you screw that on, and you're done. It literally takes about a minute once you're experienced. It's a little slower the first couple of times you do it because you're thinking, this is gonna be a disaster. But then you get used to it and it works pretty well. I can show you after the meeting for sure.
Sure.
Yeah. Yes, sir. Oh.
I noticed that in your cost analysis you did not include the computer.
Yes, that is a good point. The assumption would be that there is a computer out there somewhere.
Yeah.
It would need to be a relatively modern-ish computer that would handle the USB 3.0 well. Otherwise, you're going to get a relatively slow frame transfer, I think.
Do you recommend then that you have one that's dedicated specifically to this and not run other stuff that might be running in the background that you might be unaware of and so on? Or?
Yeah, what I read is that when you're imaging, if you want to get the best possible recording, you would basically shut everything else down during the recording part. So in other words, you fire up your planetarium program, you get your telescope pointed, and then you basically shut down that planetarium program, shut down your other stuff, and then just focus on the recording, and then tweak the capture tool to get the best frame rate with the minimum number of frames being dropped. And there's the SharpCap software. I had a very quick look at it over the weekend, and it has sort of like presets. So you can sort of say, well, if you're capturing, like one of the things that's nice about it is you can say, I want to capture, I'm going to borrow somebody's Mac here. Let's say I want to capture the whole frame. Great, that's maximum. But I can also tell it to only capture this part, or even just that little part, because that's where the occulting star that I want to see is there. And the smaller you make the relevant part of the frame, the faster the frame rate becomes, right? So you're able to actually kind of tune that a little bit, and that would also reduce the load on your computer to make it work better, right? But it's an important variable, and that's one of those things. Like I've done some basic recording, and it seemed to work, but no real life experience to share. I'm sorry.
Okay, thank you.
Yeah.
Let's say the visual magnitude you could see through a telescope is, say, 12.
Mm-hmm.
I know you don't have any feedback because you haven't been observing because you didn't want your scope to get wet. But do
Well
the-
said, well
do-
said.
Do the people that sold it or others talk about that you could see brighter stars, only brighter stars than the best visual you could get, or you could see even fainter stars? Because often I find for occultations, I see one, it's great, I'm in the path, and then I look at it and it's just right at the limit of what I can see, and there's
Yeah.
a tad bit of light pollution in Bolton, so I usually sleep.
Yeah. Well, I think, yeah, what you're saying is a kind of a common issue, and I've had occultation cameras that do a certain amount of integration, right? Like stacking inside the camera, and then so it stacks like 10 frames and then sends one stacked frame per 10 frames, and so you lose time resolution, but you get sensitivity. I generally find I can see more with the camera than I can see with my unaided eye, generally speaking. But can I see the target in question? So what I found with my existing rig, my limiting magnitude is like 9.5, 10. I'm hopeful that this can go much better. And I'm not sure how much of that limiting magnitude is just Toronto, but also, there's, one of the unfortunate things is our friends in Australia get a lot more occultations because they just have way more stars to occult, right? And so, here in the northern hemisphere, especially when we turn into like the fall, like the number of stars that the asteroids can fly in front of is significantly decreased at this time of year, which also limits your opportunities, right? So there's a number of factors that come into it, but I generally find the camera does a better job of showing stuff than my eye, especially these days as my unaided eye continues to go past its warranty.
Yeah, question from the web.
Yeah.
Is it possible to attach a DSLR to the Hyperstar?
Yes, it is. It is. I have seen it done, and it because it fits a standard T2 interface, you can certainly do that. But one of the issues is that the DSLR's footprint is much larger in terms of obstruction than these round cameras. So these round cameras are actually, I think, in some ways built with the Hyperstar in mind, because I look at the footprint here and it's, from here to here, it's just about practically identical. It's literally almost designed, it looks like it's almost designed for it, but I know a DSLR would stick out quite a bit on both sides there, and it would cause some obstruction that you wouldn't have with this camera. Yeah. Any other questions? Yes, sir.
Sure, it's no more of a question as opposed to clarification. I think the Hyperstar is recommended for 9.25 and up in the SET's models.
Is that with the new Edge, Edge ones?
Yeah, the Edge, yes.
Yeah.
I don't think it's recommended for the 8-inch.
Well, this is a model that works for, this is designed for the 8-inch, but it does have limits in the sense that it doesn't have as big an imaging surface as it would have if it was a bigger telescope. So the bigger like each one of the Hyperstars, and formerly that is sold by Starizona, I think I said that right, is sort of optimized for the size of the corrector that it has to work with. So you get a bigger field of view if you go up to like a C14. I saw on the Starizona website as well that they don't currently have any fast stars for 8-inch for sale. So maybe they're rethinking that in terms of their marketing. This system also works only on Celestron scopes. It's not something that's available with Meade. And the 9.25 model, they actually had something where the mirror is bigger than the hole that's in the corrector plate. So you literally can't take the mirror out with certain 9.25 models, because if you did, you'd have to make the hole in the glass bigger. So that is like, I didn't realize, it's like, why can't my 9.25 do this? Well, it's actually because the mirror is actually a little bigger than the corrector plate. So anyway, all that to say that, yeah, this is a bit specialized, but you could put this camera on any other telescope, right? So the ideal is to have a short focal length, but you could put it on any other telescope that it can handle. Yeah. Any other questions? Once? Twice? Well, thank you very much, everybody. I hope to come back with results.
Oh, yeah. All will become clear. In that nice amphitheater, just plopped right in there. Well, as you can see, I've been traveling again. And they call this Namibia's, is it okay? Yeah, you're okay. Okay. Namibia's fallen star, great big meteorite out in the middle of nowhere. So I've been traveling. I started in Windhoek, right here, went down near, saw the dunes, all up and around here, and ended up in Victoria Falls. But where we're going to talk about is Grootfontein, which is where the Hoba meteorite is, about 20 kilometers west of Grootfontein. So you've seen one picture of it. We'll get to some more after a bit. There's a nice national monument there that was established in 1955, but it didn't get built until close to 1990. The landowner donated the meteorite and the land to Namibia, and a uranium company donated the funds for development of the site, including that nice amphitheater that you saw in that first picture. So this is what greets you. Better not have any complaints. It's 300 miles. And they don't have Wi-Fi, so you have to talk to each other. That's a big problem anymore, you know. Also, beware of falling meteorites, especially that one. Okay, so we all know what some of these things are. The asteroid's just going to pass by Earth. If it burns up, it's a meteor. If it hits the ground, it's a meteorite. It just stays there. It's Congress, right? Called Congress. Or maybe Parliament. Okay, now this is not to show that I was there, not proof of purchase or anything like that, you see. It's just for to show how big the meteorite really is. Okay, here's some statistics on this thing. Discovered in 1920, it's about 3 by 3 by 1 meters, weighs 61,000 kilograms. Age is, 4527 plus or minus 29 million years, and that was estimated in 1996, fairly recently, they came up with that site. It's a nickel-rich group 4B ataxite. There's only about 14 of these meteorites of this age that are known to exist. And this is one of them. So it's 82% iron, 16% nickel, and around 1% other elements, mostly cobalt. And that provides something interesting later on. The Smithsonian Institute scientists concluded that the meteorite had been present, quote unquote, on the surface of the Earth for about 80 to 300,000 years, and that a layer about 27 inches thick was removed from the meteorite by ablation when it passed through the atmosphere. And that comes from Fernie. Somebody might recognize that name here, but we'll talk about that later. Things of note, Hoba from the native language means gift. It's the largest known single-piece meteorite in the world. It's the most massive naturally occurring piece of iron known on Earth's surface. Not surrounded by a crater. Its remarkable flatness of its bounding surfaces, unique among meteorites. One theory is that the meteorite shape caused it to skip along the surface of the Earth rather than crashing and burying itself. I guess like skipping a rock across water, but that's a pretty heavy one. So there it is. I just walked around it. It looks pretty much the same all the way around, starting here at, starting here at the steps. This is just side 1, side 2, side 3, side 4. It's all pretty uniform. So some analysis was done on it right away after discovery by a non-scientist, but he was very detail-oriented. And they found elongated patches of troilite, which is a rare iron sulfide. Most common mineral on the lunar surface is troilite, and it's also present in Martian meteorites. These Wittmann-Statten lines that are very often present in meteorites of this type are absent in this one. But there are some Newman lines that are present. These are just example photos. They're not from Hoba. Okay, vandalism used to be a problem, but it's very hard to do because of the composition of the meteorite. Why? A nickel-iron mass with just a touch of cobalt results in an alloy of unexpected toughness, you know, even if it is fairly ductile. So those are examples, up-close examples of where vandals have tried to get a piece of this meteorite. Somebody asked me if I brought home a piece of it. No way. You're not getting anything off of that. There's an interesting story here. The South African company donated to the British Museum a piece of this meteorite. But getting it off the meteorite was a real chore. It took 2 days for 2 natives working all the time with many hacksaw blades to get off a wedge-shaped piece about 2,500 grams and about the size of a sheet of paper, fairly small sheet of paper. And this is from Spencer from the British Museum, who then performed a thorough analysis of the specimen. The meteorite has, unfortunately, been disfigured all along one top edge by some stupid person with an oxyacetylene blowpipe. So it's tough getting a sample of that meteorite. They only seem to be 18 pieces of this in collections around the world, only totals 25 kilograms out of 61,000. So it's hard to get at. Okay, here's a little bit of the history, and this disagrees with what you find on Wikipedia. But this is an actual tale that the man who found it told, and it's in the museum in Grootfontein. He was, Wikipedia says that somebody was out plowing and they hit it with their plow and found it. He was out hunting. He noticed the strange rock, sat down on it, tried to scrape a little bit of silver under there. So he thought he got just enough off that he took in to Grootfontein. where mineralogist established it to be a meteorite. So he came home and they talked about it, and he went on with his work, and Mrs. Britz started excavating it. So she started digging and got quite a ways around digging it. So they weren't the owners of the farm where this was found. Hansen was. And after he heard about the discovery, he now claimed to be the discoverer. So he wrote to the museum saying, "I have discovered on my farm a huge meteorite, and I have digged a trench round it to find its thickness." So he wanted somebody to put a value on it. The museum replied in a rather condescending tone, "One cannot quote a price as one can for sheep or cattle." Okay, these are just some kind of random photos. This is thought to be the first photo of the meteorite. No date on that. Once the knowledge about this meteorite spread around the area, it got other people coming just to take a look at it. This man here is Spencer, who was very involved in analysis of this. And this is the International Geological Congress excursion in 1929 to see it. And this is Gordon, who did the analysis on it that I've already talked about. He was the second ever scientist to visit the meteorite in 1929. So even the New York Times gets in on this in 1929. And particularly here, again, chance has led us to the discovery of one of those mysterious messengers that come to the Earth, bearing evidence that space is not empty, but is populated with a vast multitude of small fragments. So this was in 1929. So now, who knows this man? Does anybody know for me? I thought Ralph. Anybody else? I figured Ralph would know. Okay, I just kind of came across this. He was a Canadian astronomer based at the DDO who'd been in Cape Town during the mid-50s. Well, he went back in 1966, and he and a friend drove by car, not 4x4s. And even today, on my trip, those roads are rough. You know, there aren't that many paved roads. They're rough roads. So that must have been quite the trip. And he published this article in the RASC journal, 1967. I didn't find this article until about 2 days ago. I was going to ask you if you knew how to get a hold of it, Tom. But I did finally came across it, and I haven't had time to read the whole thing. It's very interesting. He took what was considered to be the first color photograph of the meteorite and said that among the major meteorites known on Earth, few can have received less attention than the Hoba meteorite. And that's probably true, because this was in 1976, discovered in 1920, a long time in between there. They established the site in 1955, so it took a long time for people to come to the party on this meteorite. So he was president of RASC from 74 to 76. I had to consult a thesaurus for making this presentation, but he was no help at all. Often at a loss for words. Okay, so these are a little off subject, but sort of close. There's only 2 touristy photos, Paul, so. This is in Swakopmund. It's on the Atlantic coast, and this is the world's largest quartz crystal cluster on display. I thought it was pretty interesting. 14,000 kilograms, 520 million years old. This is, This is my photo here. I stole off the website because it gives a comparison of the size. It's big. You know, it's fascinating to just come up and look up at this thing. Okay, people have asked me since I came back if I did any observing while I was there. Well, kind of, sort of, one night, sort of. This is my place where I was staying at night. It's on the banks of the Quando River. You can see the river out there. Right in front of the hut, there's a deck there. But I walked out after dinner one night about 9 o'clock and was coming back to my lodge. And this path here is patrolled at night by a guard, back and forth, because there are no fences and there's wildlife around. And we had just been watching crocodiles and elephants and hippos across the river there. So I looked up and I thought, oh, this sky is glorious. I have to just find some place to look up at it. But there are lights on the path. But I found this little corner right here on my deck where this tree blocked the light. So I took a chair out there and I sat there for about a half an hour looking up. Not a good sight. I'm facing east there. There's not really, Mars is up here. Planets are over here. Until, about a half an hour I'm there, until all of a sudden I hear a splash and some rustling in the bushes. I was back in that lodge in about 5 seconds, leaving the chair. So that's my observing in Namibia experience. So just a few touristy photos. This was on an airplane flight over the coastland near Swakopmund, and those dunes look like that. They look just luscious. It looks like frosting. They're just gorgeous. Okay, here's a moon. It's a moon set over Etosha National Park. That one's taken with an iPhone because my camera lens went out on me halfway through this trip, my wide-angle lens. There's my pelican sunset. Thousands of pelicans we saw there. Pelicans. And there's my hippo sunset. So the sunsets are kind of relevant to astronomy here. Okay, so I did some digging around too to prepare this presentation, but not quite like Mrs. Britz was doing. Not digging in the dirt too much. This, I've been told, is an African goodbye. That's all, folks. Thank you for listening. So, you can close that. So how do I get that off? Any questions? Nope. Adrian.
Coolest places on Earth. Well, what was your reasoning behind going on this trip? Because normally you do astro trips, like Chile, for example.
I've always wanted to go south in Africa, and particularly Namibia. It's just always been one of those dreams to do, and this trip came up that took me exactly where I wanted to go. I saw everything I wanted to see, in 4 weeks, Had a fabulous time. Mainly animals and pretty scenery, few stars. So, anything else? Okay, thank you. Okay.
Hi everyone, my name is Artash.
And my name's Arushi. So, a few weeks ago, we made a project called Deep Space Musical at the Space Apps Toronto. That's actually a hackathon, so you have 48 hours to solve a challenge. So, what our project does, our project takes an image from Hubble and converts it to music so that the visually impaired can also enjoy the beauty of the universe. This project actually won the NASA Space Apps Award.
Hi, so we all know the Hubble Space Telescope. The Hubble Space Telescope is launched in 1990, is actually gonna turn 28 this year. And it's been taking over 1.3 million observations so far. So, and many of these observations we've already seen, like popular ones being the Pillars of Creation, or it's a visual telescope. And so, since its pictures are so interesting, we thought it would be a good idea to actually turn these pictures into music, so we can experience the universe in a different way. And the best thing, of course, is that it's people who are visually impaired and can't actually look at these images can also enjoy the beauty of our universe. So these are just a couple of the pictures taken by Hubble. So how did we convert this image into music? Well, first we took the RGB color image from the Hubble Space Telescope, in this case the Pillars of Creation. So then we took this image and converted it into grayscale. There. So after converting to grayscale, this is still a pretty big image, like thousands of pixels inside the image. And we can play each of these pixels in the image, because otherwise the music will be way too long and there'll be many non-eventful parts in the image. So after this, I performed something called pooling on the image. So basically what that does is it resizes the image here into a smaller image. But at the same time, it'll keep the main details inside the image. To do that, basically I take maybe of the grayscale image, I take a small part, and then I take the largest pixel value inside that part. And I repeat this for every this part, until I get a condensed image, this one. So to do this, I used Python, a programming language I use a lot.
So what I did is I took the numbers that he gave me, and then I assigned them a musical note so that you can actually play the music and then see the notes.
Yeah, since basically I had a matrix of many different pixels, I gave those pixel value to Arushi, and then she was able to convert them into frequencies, basically musical notes. So basically how it works is that each pixel in the image is played one by one. So first, the top corner pixel is played, you hear the note, and the brighter the pixel value, the higher pitched note you'll get. So our musical has 3 parts. The first part, of course, being the birth of the stars. So stars are born in, for example, nebulas, and so one of the very popular images is the Pillars of Creation. Basically, it's a bunch of gas inside the Eagle Nebula, M16, and that bunch of gas looks like a couple pillars, and it actually becomes lighted up, as you can see in this image, because of the radiation coming from the nearby hot stars. So now, I'm going to actually play the music for this image. So before I play it, you'll notice that since we're playing each pixel, you'll notice that when we hit a higher pitch note, it means that we're reaching a star, like here or here. Of course, these stars are not actually inside the dust cloud. We're just seeing them because, well, they're much closer to us than the pillars of creation. So I'm going to play the music. Yeah, so that's a short example of the music, a little bit of the music. So you can see that there are not many sharp notes because, yeah, in this image, it's mostly just the big gas cloud, which is pretty much the same color and brightness. But each time we hit one of these stars, we get a higher pitched note. So the next image, after the stars are formed, then, of course, they'll form into galaxies. So this is a picture from the Hubble Ultra Deep Field image. So this was taken over a period of 2 weeks, actually, to get a good exposition. And so here's the image. There, it's basically a lot of clusters of galaxies. So now, in this image, unlike the previous ones, we don't have only a couple points of interest. We have many, many different galaxies. Actually, in this image, there was actually 10,000 galaxies that we could count. So now I'm going to play the music, and you'll notice that higher pitched notes are much more frequent now. Yep, there you go. And then the last part of our musical will, of course, be the death of the stars. So, this is the supernova 1987A. So this used to be a blue hot giant star. And, since blue stars don't actually live very long because they consume their energy much faster, being much hotter, it started slowly shedding out its outer layers of gas. And then eventually, so the gas was kind of forming a ring around the image. But then the supernova happened, of course. So a lot of radiation and a shock wave was burst out of the center of the star and then collided with the dust and the gas that had been released out of the star previously. And that's what lighted up those rings of gas around it, so we can actually see it when we look through it, the Hubble. So now I'm going to play you this image. But, since the rings are lighted up by such high-level radiations, it's going to be very bright. So you're going to hear lots of very high-pitched notes in this image. So yeah, as you can see, so slowly what happened in this image is that it came here, it was pretty low-pitched sounds, and then suddenly it got much high-pitched, and then continued with high-pitch, low-pitch, high-pitch, low-pitch. So now that you've listened to a bit of each individual part, I'm going to play you the whole musical. So around 40 seconds from each image, so you can actually hear the whole thing together. Kind of how everything formed, galaxies, stars, galaxies, and the death of the stars. Now, last one. And that is the whole musical all together. Thank you, and we would also like to thank the Royal Astronomical Society of Canada for keeping everyone excited about space and astronomy. So also this year has been very special for us. We've participated in many RASC events this year, and we continue to mention the Royal Astronomical Society of Canada inside our many presentations that we do and on our website. So this year we've won the Jesse Ketchum Award, and we've done many other presentations.
Yeah, I spoke at the Women in Planetary Science for women, and yeah.
And thank you.
Borrow the microphone so we can ask the question.
This is probably silly, but what does the 80 on your note staffs mean? It had number 80.
80?
On the where your notes are.
Oh, here?
There's no.
Oh.
80.
Oh, here?
Tempo?
Well, yeah. So we since we're playing notes in each of the parts in the musical, we just Arushi converted a small part, a small part of the beginning of each of the musical for each image into notes actually. So for the first bar here, these are a couple of notes that are played in the first image of the Pillars of Creation. Here, same thing. But you can see the notes are changing a lot. And last one, where you can see you're getting really high-pitched sounds.
First of all, I'm extremely impressed. This is amazing. The other question is, have you thought about condensing the three parts, if you like, into three voices in a three-part harmony so that they would play simultaneously, and how that would sound?
Yeah, we've not thought about that, but it could be interesting. But we did it like that because these three images, they form a sequence together. So the first one, the birth of the star, the forming of galaxies, and the death of the star. So we just thought it would be more rhythmic and sequential if we put all three images, 1, 2, and 3.
You mentioned that you won a NASA app competition.
NASA Space Apps, yep.
Space app, right. So what is the next stage then?
Yeah, so we won the NASA Space Apps Toronto this year with this project. So the next stage, since now we're a global nominee, we still had to submit a 30-second video to NASA, and then they'll be looking at all the videos and selecting some of the best.
Very good.
Thank you.
Something rather boring, and I have to talk about the election. No, not that one, but the one that's coming up in a few weeks. We are about to release the slate of candidates for. I want just to be announced to anyone here or anyone online that we are now accepting nominations from anyone in the Toronto Centre. If you'd like to join council, you require 2 signatures from members in good standing on your nomination form. Just hand it in to myself, the head of the nominations committee, or President Ralph Chu, and you have until 2 weeks before the AGM. Thank you. Oh, the AGM is December 12th. So I will be making other calls on the forum. The only problem is that because we only have one other meeting before the AGM, and that is our fairly large speaker night, I figured we might not have a chance to make this call at that time. So that's why I'm doing this now, just before we've released the nominations has released. We'll release the slate of candidates. We'll be doing this on MailChimp in the next few days. Ralph?
Meeting in 2 weeks' time is a speaker's night, and our speaker that evening is Professor Rainer Weiss from the Massachusetts Institute of Technology. Professor Weiss is a Nobel laureate in physics for 2017 for his role in designing the LIGO observatory. And he'll be talking about exploring the universe with gravitational waves. Now, all members who have a valid email address got a message from me by MailChimp with a link to a special web page on our website where you can register for up to 2 tickets for free. We have an allotment of 200 seats in the auditorium for this particular lecture, and you need to register for those in advance. We will be closing the list off when we either reach our full allotment of tickets, or if let's see, I think the Science Center's cutoff date is November 22nd, because we have to print the tickets. So the idea will be that when you arrive on the evening of the talk, you'll go to a special reception desk in the front building, and they'll have your name on a list and just give you a ticket at that time. Okay? Because it's a public event and the other 200 tickets are being sold to the general public, we're all going to have to pay for parking. So it's $5 for the car to enter the parking lot for that evening. But I'm sure it'll be an interesting talk. The moderator for the conversation after the lecture is Sarah Seeger, and she's coming up with Professor Weiss from Boston especially for this talk. So it should be a really great event. Okay, our next meeting after that is 12th December, which will be the Recreational Astronomy night, our last meeting for the year. And we'll have a short presentation that evening, Chris Vaughan doing Sky This Month, and Clay Davies talking about building a Newtonian telescope for visual wide field and air travel. I can hardly wait to see what he's got in store for us. And then following Clay's talk, we'll have a brief intermission while we set up for the annual general meeting. And that's where the election comes in. We have a number of councillors as well as members of the executive whose posts are up for election this year. And again, if anybody's interested in being nominated for a position, you can talk to either Tony Horvatin, who's the chair of the nominating committee, or myself, or to Tom about that particular bit of work. Okay, next solar observing is going to be on November 24th, and in the usual way, Sean will give the go or no go on that either Friday evening or first thing Saturday morning. And I think this is probably the last of the solar observing sessions for the year 2018. What we've decided to do, we were trying this out this year to use full moon weekends or weekends near full moon, with the idea that that would free up people perhaps to do other things other than come out to the telescope for solar observing. But it's been a moving target. It really hasn't made anything any easier, I think, to get volunteers or do anything else. So we're going to go back to the first Saturday of each month starting in January, and that'll be a bit more predictable, hopefully. So again, Sean will be making the announcement, and thank you very much for all the work in organizing these events throughout the last few years. Okay, the other monthly observing events, I'll call your attention to, the City Star Party, the week of 12th to 15th of November. The first clear night next week will be the City Star Party at Bayview Village Park. And then we have a long wait till the next Dark Sky Star Party, first week of December. Again, first clear night. And again, there will be a no-go or go announcement on our media and the website in the usual way, probably in the late afternoon, to just let you know whether those events are going ahead. Car Observatory still operational. Ian Wheelband is up there this evening getting ready to do a library talk in Thornbury. The road's still open, at least for a little while, but once the snow flies, again, we'll go to winter mode, and that means that you park at the top of the hill on the road that runs in front of the observatory and then walk in because they don't clear the snow from that roadway during the winter. So it's still available, but you do have to do a little bit of walking. If you don't want to do that and you're interested in getting a look at some new equipment other than for hyperstar adaptations and so on, we do have a number of instruments available for loan, and again, we have a couple of our telescope loan managers, Mark and Peter, here tonight. If you'd like to talk with them about borrowing equipment, please feel free to do so. And finally, the usual invitation for the meeting after the meeting at the Granite Brew Pub down at Mount Pleasant in Eglinton. Please feel free to join a few of us down there after the meeting ends. So again, we'll see you in a couple of weeks, either here in person or online. Remember to get your tickets for Professor Weiss's talk online, and please be patient about it, because we are in the we've unfortunately gotten to the stage where we've had to upgrade the service on our website, and there's apparently been a bit of a mixed up on the links between that website and the national website where we validate your memberships. So if you cannot get onto the website to register for the tickets, try again in a day or so. Hopefully by then we'll have that technical problem solved, and we'll see you here then or online for Professor Weiss's talk. So have a safe trip home, everybody. See you in 2 weeks.